In this question, we're given a phase diagram and some information about the phase diagram, and then we're asked to interpret some different properties of what phase the substance will exist in, and we'll do that in a second. But first, I want to discuss the phase diagram briefly. A phase diagram has pressure, in this case in atmospheres, on the y-axis, and the temperature, in this case in Kelvin, on the x-axis. At low temperatures, so far over here on the x-axis to the left, and anything but extremely low pressures, the substance exists as a solid. At extremely low pressures, very low on the y-axis, and temperatures that are very high, very far to the right on the x-axis, the substance exists as a gas, and at intermediate temperatures and pressures, the substance can exist as a liquid. You'll note that this is called the triple point, the temperature and pressure at which all three phases can exist, and this is called the critical point, where you can end up with a supercritical fluid. So let's take a look at the questions here now that we've talked about a phase diagram a little bit. It says, suppose a small sample of pure X is held at minus 237 degrees C and 1.8 atmospheres. What would be the state of the sample? Well, first thing we have to do is realize that the temperature here is in Kelvin, not in Celsius. So we need to add 273 to this and realize that this is 36 Kelvin. So we need a temperature of 36 Kelvin and a pressure of 1.8 atmospheres. 1.8 atmospheres is about here, 36 Kelvin, and it's right about between the middle of these two lines. So we have where the blue dot is, this is the temperature and the pressure that we're looking at. And we're asked for the state. Well, that's a pretty easy question. Once you find the temperature and pressure, this is clearly a solid. Now it says, suppose that the temperature is held constant at 36 K or minus 273 degrees C, but the pressure is decreased by 0.7 atmospheres. What will happen to the sample? So we want to decrease by 0.7 atmospheres. Notice that each of these boxes is half an atmosphere. So we want to go a little bit more than a box down to about 1.1 atmospheres, which is about right here. So we started at about 1.8 atmospheres and we went down to about 1.1 atmospheres, and we're still in the solid. So what happens to the sample? Nothing. As far as phase change, nothing actually happens to the sample. In the next case, it says, suppose on the other hand, the pressure is held constant at 1.8 atmospheres, but the temperature is increased by 115 degrees C. What will happen to the sample? Well, notice that a temperature change of 115 degrees C is also the same as a temperature change of 115 Kelvin. So if we add 115 to 36 Kelvin, we get 151 Kelvin. So at 1.8 atmospheres, and this is 151 Kelvin, we go from here to here. Now we've crossed the barrier between the solid and the liquid. This is called the fusion curve. Fusion meaning in chemistry melting. So this is the fusion curve. So we've gone from a solid to a liquid, which is called melting. So we have melted the sample. So by finding these specific points on this phase diagram, we can figure out some information about what phase changes, or in this case no phase change occurred, what will happen to the sample.